Good morning, students.
Good morning, sir.
Am I audible?
Yes, sir.
Yes. Yes, sir.
So, who has logged in as OG Shrika? Please rename yourself to original name. Okay, perfect. We'll get started. Yeah. Yes. Students, just give me a second. My Zoom is not responding. So I hope you're able to see my screen, right? Is everyone able to see?
Yes, sir.
Very good. Okay. So before I start with today's class, let's just recollect the names of the topics that we have learned and the objectives of all the topics. Okay. So what did we learn in our 12th standard? Chapter 1. What was it all about? It was all about electric charges and fields. Correct? So what did we deal in this chapter? Can someone tell me? So in electric charges and fields, what was our main context of discussion?
Electricity from static charges.
So we were mainly concerned about the field, right? The main context we would have concentrated here is electric field. And if there is a question asked, what is the source of an electric field? What will you say?
Static charges.
So, very good. So source is static charges. Be more precise, you can even say charges. Generally, if there is a charge, then you can assume there is an electric field around it. Okay. Similarly, in chapter 2, what did we learn? We learned about electrostatic potential and capacitance. See, there is a reason why I'm discussing all these things. Listen to this carefully and try to answer. Okay. So when we discussed about electrostatic potential, what was our main concentration upon? We discussed about this concept itself, and we tried to understand what is the relation between electrostatic potential and field. Right? We try to understand. So how these two physical quantities are related and how they can help us understand certain phenomena in the next chapter. Right? So if you ask me, what is the necessity of us knowing electrostatic potential? Because in current electricity chapter, we were concerned about the potential difference and all those things, right? To make the charges move. So what were we discussing in chapter 3? We were discussing about
charges.
current, electricity. That is how to put the charges in motion. So what did we understand? So how can you put any charge in motion? By applying potential difference. So when you apply potential difference, what will happen? There will be an electric field created due to which the charges will start moving. That is chapter 3. So what did we discuss in chapter 4? That was moving charges and magnetism. So what do we mean by moving charges and magnetism? What was this chapter all about?
Magnetic field lines produced by electricity or by charges.
Is it magnetic field or only magnetic field?
Magnetic fields, sir.
Yes. So here we understood that moving charges create magnetic field. Okay. So these are the 4 main contexts I wanted to discuss, especially the first one and the 4th one are very, very important to us. Now there are some important questions that we need to start asking. The question is, here we told we are going to generate electric field, except now the question is this electric field a parameter dependent on time? Means, does the value of this electric field change with respect to time? Did we discuss anything like this in that chapter? Suppose, try to understand my question. If I have a point charge here, there is going to be a region of electric field in all the directions like this. Right? Is this electric field a parameter dependent on time is what I'm asking. Suppose I take a point here. If I say the electric field at this point is E1, like you come after 10 days, you look at the same charge, let's assume it has the same amount of magnitude, nothing is lost to the surroundings. If you measure the electric field at point P, do you think the value of E1 is going to change with respect to the time of 10 days? Or is it still going to be the same?
Will still
Even a
be
while,
the same, sir.
it'll still be the same because the strength is same and what else is the same? The distance from the charge at which you're trying to measure the electric field is still the same, because we know for electric field E is equal to Q divided by 4 pi epsilon naught R square. Correct? So it is still going to be the same. In a similar way, if you talk about putting a charges in motion and measure the value of magnetic field, is it going to change with respect to time? That is, if you have a current carrying conductor and there is a steady state current which is flowing through this, and you want to measure the magnetic field at a point P which is at a distance R from this current carrying conductor. It is going to be mu naught I divided by 2 pi R. Right, this is the value of magnetic field. Is this value going to change with respect to time? What do you think?
Sir, will I be constant here?
Yeah, I is constant. It's a steady state current.
Then it will be constant, sir.
It is going to be the constant because everything else is a constant in this equation, right? So what we are able to understand from these two things, that electric field and magnetic field, if you try to measure them with the same source at the same distance of separation between the source and the point where you're trying to calculate the field, it is not a time dependent quantity. Correct? Which one? Electric field and magnetic field. These both are not a time dependent parameters. But here comes an important question. What if I'm interested to make it a time dependent parameter? What am I supposed to do to achieve that kind of a stuff? is what this chapter is all about. And that is why the name of the chapter is anybody. Can you tell me what is the name of the chapter number 8?
Alternating currents, sir.
No, alternating currents is 7th. Alternating currents is 7th chapter. So the topic that we are going to discuss today is 8th chapter, and it is named as Electromagnetic Waves. Okay. So if you look at the name itself is suggesting something. This term electromagnetic waves is not something new to you. You would have already learned in some context in atomic structure. Let me just recollect what will happen. If you recollect the Bohr's concept or Bohr's structure of atom, there is a concept like this, right? There is a concept of orbit, n is equal to 1, n is equal to 2, something like this. If you take a hydrogen atom in its excited state, or a hydrogen-like atom in its excited state, what will happen? If there is an electron in the second orbit and it is jumping to the first orbit, what will happen? You would have learned this. You know that whenever, this is a very common thing, right? Whenever an electron jumps from a higher orbit to a lower orbit, what is going to happen? There is emission of something.
Energy is released, sir.
Yes. There is emission of some energy, and that energy is released in the form of electromagnetic waves. You would have learned about different series, right? Lyman series, Balmer series, Paschen series. I'm not sure if you guys remember this, but you would have at least heard this, right?
Yes, sir.
Right, you would have heard this, right? So, depending on what kind of an electromagnetic wave is released by the transition of electron between different orbits from a higher to a lower orbit, what will happen is the series is confirmed as different types of series, like Paschen, Balmer, or whatever you call it. Okay, and remember that energy is released in the form of electromagnetic waves, and that is what we are going to discuss in this chapter. So, two important points I want you to keep strongly in your mind is, by now you should have actually done it, that the source of an electric field is a static charge, or for that matter, charge itself, and the source of magnetic field is what? The charge is in motion. Now comes an important question. Here I'm calling electromagnetic. So if I try to break it into two fields, electromagnetic is nothing but a combination of electric field and magnetic field, along with a factor where these two fields are time variants. Means our job in this chapter is to make a combined electric and magnetic field which is changing with respect to time. Since it is changing with respect to time only, it is not called as electromagnetic field, rather it is called as waves. Because what do we mean by waves? So what do we mean by waves? Anybody, try this. So what do we mean by waves? It is the energy transferred from one place to another in the form of a disturbance. Or I can say with the help of a to another with the help of a disturbance, right? So I need to discuss certain important factors here. I hope everyone is concentrating, right?
Yes.
So energy transferred from one place to another with the help of a disturbance is generally called as a wave. So can you guys tell me the classification of waves? So classification of waves, all these things are from 11th standard. I'm just recollecting all those things. So how are waves classified? Basically dependent on two parameters, the way they propagate and whether they require a medium or not. So depending on the medium, okay, waves are basically classified as mechanical and non-mechanical. So basically, what are mechanical waves? Mechanical waves are those waves which require medium. So non-mechanical waves are those which do not require medium. Okay. Can you give me an example of mechanical waves? What are all the waves that you know that require a medium to propagate?
Sound.
Very good. Anything else? Water ripples are there, right? They are also wave. Right. These are all the waves which require a material medium for their propagation. Propagation means traveling. Okay. Can you give me an example of a non-mechanical wave?
Light waves.
Yes.
These
So
electromagnetic waves, sir.
yes. Light itself is an electromagnetic wave. I'm talking about the visible light. Okay. So the visible light itself is a subset of electromagnetic waves. Okay. So here, what are the types of waves that you're trying to deal with? We are trying to deal with a non-mechanical wave. Have that thing in your mind first. Okay. Please write down this point. Let me know once you're done. So done with this, I'll go to the next concept.
So for non-mechanical, you wrote as light, visible light, as well as the light produced by electromagnetic.
You take light. You take light. We are mainly going to discuss about visible light in our syllabus. But other than light, you have this infrared waves. Okay, you have radio waves, microwaves. All these things are there, right? All those things fall under the sub context of electromagnetic waves. Out of which one of the important concepts that we know is visible light. So visible light is an example of non-mechanical.
Okay, sir.
Okay,
That's
done. Good.
yes, sir.
Good, good. Okay. So the next classification is based on the direction of vibration and propagation. Okay, direction of vibration and propagation. They are basically classified into two types. One is called as transverse, and the second is called as
Longitude.
very good. They are called as longitudinal. Okay. So what do you mean by transverse? Transverse generally means perpendicular. Longitudinal means parallel or anti-parallel. So if direction I'll write it as DOV, okay? If direction of vibration and direction of propagation are perpendicular to each other, then we call it as a transverse wave, okay? If direction of vibration and direction of propagation are parallel to each other, then we call it as longitudinal. So example is, light is a transverse wave, whereas sound is a longitudinal wave.
Sir, a doubt, sir.
Yeah, tell me.
So this light we are seeing in transverse wave is the same light in non-mechanical, right?
Yeah, the same. So basically, if you're trying to talk about light, you can actually club these two classifications together in the sense light is a transverse non-mechanical wave. And this is a very, very important point because there is a point based on which the next two chapters are dealt on. Okay, it is not only the next two chapters, even in the 12th chapter, I told you about the atom jumping from one orbit to another, right? There also we'll be discussing these things. So you should have a clarity. So whenever I'm trying to talk about light, light is a subset of electromagnetic wave. And what is the basis? What is the classification of it? It is a transverse wave, means the direction of vibration and the direction of propagation of light will be, particles will be perpendicular to each other, and it is a non-mechanical wave, means light doesn't require any material medium to propagate. So it doesn't mean that if there is a medium, light will stop. No. Basically, it does not require a material medium to propagate, but if there is a medium, it will still travel through it. Like how we are able to live, right? We are able to see light. Okay. Rohan, I hope I answered your question.
Yes, sir.
Okay. So shall we get into the context? Now I have to show you how exactly an electromagnetic wave is going to look like. Okay. So what did I say light is? Light is an electromagnetic wave. Right? Now try to connect all the dots. So when I talk about an electromagnetic wave, what is it supposed to be? It is supposed to be a transverse wave. Right? So if there is only one particle vibrating, if there is only one field and it is able to travel, then it is easy for me to show how an how a transverse wave looks like. But in this case, what is happening? You have two fields. What are they? Electric field and magnetic field, which are time variant. Correct? So let's see how exactly an electromagnetic wave looks like. Look at this. So look at the GIF, no? Look at the GIF. Are you able to observe something? I'll give you a minute time. Just observe and tell me your observations. Just look at it. What is that you understand?
The electric field and magnetic field is perpendicular, sir.
Okay, that's
The
right.
displacement vector.
They change the direction periodically.
Okay. They're changing the direction periodically. And
The horizontal distance between the two waves are like same, sir.
Horizontal.
Successive waves are same, sir.
Okay.
That crescent
what-
and trough, I think, sir. Crescent and trough,
Okay.
something.
Crest. It's called crest and trough.
Yes, sir. Crescent.
Right. So two important observations. You can see that the electric field of this particular wave that is shown here is confined to which direction? It's a very good observation that you guys told, but I'll ask you some more questions. So the electric field in this case is confined to which direction, guys?
Confined to XY plane, sir.
Look at the direction of electric field, no? The electric
Vertical
field,
up and down.
what? Up and down is fine. Up and down is confined to which axis?
Y-axis.
Y.
Correct. So here electric field is confined to y-axis. So for it to be called as an electromagnetic wave, the magnetic field should not be confined along y-axis. Logically, right? Because what did I say an electromagnetic wave is? Electric field and magnetic field are perpendicular to each other and they are time variants. So since they are time variant only, if you see the magnitude of electric field, it is changing with respect to time. Look at the arrow mark size, no? It is becoming smaller to maximum value. Right? I hope you're able to understand this point. So since electric field is fixed in the y direction, magnetic field can take either x direction or z direction.
Z direction.
So in this case, what has happened? They have taken the magnetic field along the
Z direction.
z direction, and for it to be a transverse wave, okay, see, there are two important points I'm trying to talk about. Listen to this very, very carefully. For it to be called as an electromagnetic wave, electric field and magnetic field should be perpendicular. Both are satisfied. And they are time variant also because they are moving. Okay, that is for them to be called as an electromagnetic wave. For it to be called as a transverse wave, what should happen? The direction of propagation and the direction of vibration should be perpendicular to each other. Since electric field is confined to y direction, magnetic field is confined to z direction. For it to be called as a transverse wave, in which direction is it supposed to propagate? Propagate means in which direction is the wave supposed to move?
And the resultant direction, sir.
That is x direction, perpendicular direction. So what I'm trying to say is, listen to this carefully. So electric field is confined to y direction. Magnetic field is confined to z direction. So y direction is for electric field, z direction is for magnetic field, and x direction is for propagation. So what I'm trying to say is, electric field is perpendicular to the direction of propagation, accepted, hence it is transverse. Magnetic field is perpendicular to the direction of propagation, again it is transverse. And electric field and magnetic field are perpendicular to each other, hence it's an electromagnetic wave. Okay, are you able to understand? So you might think it is a very simple point, but questions can be asked based on this also. So listen to this very carefully. So if the electric and the magnetic fields are perpendicular to each other and they are time variant, along with the satisfaction of the factor that electric field and magnetic fields travel perpendicular to each other in the direction of x in this context, then this is how an electromagnetic wave looks like. Okay, so what is our job in this chapter is to understand how to produce this kind of a wave. First thing, if this kind of a wave is achieved, then what are all the equations we need to give so that we can solve problems easily? Okay. So in this chapter, more than problems, it is more of theory only. But yeah, we'll discuss as time progresses. Am I clear till this point, guys? So with all this knowledge, I'm going to start the main context of this chapter. Shall I start?
Yes, sir.
Oh. So write down this point, electromagnetic waves. So first we will understand what an electromagnetic waves. A changing, I told you, right? A changing electric. Okay. Here I got into the context directly. Listen. First, let me read the statement, then I'll explain what it is. A changing electric field gives rise to a changing magnetic field and vice versa, which gives rise to a transverse wave known as electromagnetic waves. Okay, listen to this statement carefully again. A changing electric field gives rise to whom? A changing magnetic field. And vice versa, in the sense, if there is a changing magnetic flux, that gives rise to a changing electric field. I'll relate both these concepts. Okay. If these two things are happening simultaneously, they give rise to something called as an electromagnetic wave. Okay, let me explain this point. So, when I asked you what is the context of the topic in the 4th chapter, if there is a current I flowing and there is a point P present here, which is at a distance R, then the magnetic field is going to be what? Mu naught I divided by 2 pi R. Correct? Now, where is this I coming from? What is the source of this current? It is potential difference. So only when you apply potential difference, you will be able to generate current. But when you apply potential difference, what is happening within a conductor? There is a generation of electric field. Guys, are you able to understand what I'm trying to say? If you take a conductor, if you apply a positive terminal here, negative terminal here, whatever is the electron, that electron will start experiencing a force of small e into capital E from higher to lower potential, where this capital E stands for the electric field directed from the positive terminal to the negative terminal of this battery. Accepted.
Yes, sir.
Right. What will happen if I am able to change this electric field? How will I be able to change this electric field? I cannot do it on its own. I will be able to change this electric field if I change the potential difference. Okay. Means if I apply an alternating source, listen to this carefully again. If I apply an alternating source, can I say that there is a time varying electric field? Right. So there will be a time varying electric field. When the time varying electric field is taking place with respect to, so when there is a time varying electric field existing, can I say that the current is also changing with respect to time? Right. So current is basically what? The amount of charge flowing per unit time. When the force with which the charges are being pushed is changing with respect to time, I can obviously say that the current is also going to change with respect to time. When that is happening, can I say that the magnetic field is also going to change with respect to time? Correct.
Yes,
right. Now, this is what the first statement means. A changing electric field gives rise to a changing magnetic field. I hope I explained this point. Right.
Sir, sir.
Yeah, please.
So the electric field changes because we are changing the potential.
That's right.
While the magnetic field changes because due to the potential change, current changes as well.
Current changes. We know, right? We know the fact that alternating current gives rise, alternating voltage gives rise to alternating current. That's what we learned in 7th chapter. Right?
Yes, sir.
That's right. Whatever you asked is 100% right. So they are all interrelated concepts. That is why I asked what we do in the 2nd chapter. Now we are able to understand why we actually learned about electrostatic potential, because electrostatic potential is such an important factor because in terms where it can impact the electric field itself. So that is why these two are very much related concepts. This relation maybe you would have not used most of the time, but you should remember E is equal to minus dV by dr. So we know this, but we have to think about this. Okay, it is because of the change in potential. What will happen is there will be a change in the value of electric field also taking place. Okay. So is there any other doubt? Shall I proceed to the next point?
Yes, sir.
Second point says vice versa. They finished it in one step, in one word, in fact. Right. So what do you mean by this? It says that if there is a changing magnetic field present, then you can have a varying electric field. When is this going to happen? When I talk about varying electric field, you can even talk about potential difference. So now let's logically think of one factor. If there is a change in potential, if there is a change in magnetic field taking place, will I be able to generate EMF? I've already put the question. If there is a change in magnetic field, will I be able to generate EMF? I'll give you a hint, 6th chapter. So what does the 6th chapter mainly concentrate upon? Electromagnetic induction. If there is a change in flux taking place with respect to time, what will get generated? There will be an EMF that will get generated, correct?
Yes, sir.
Right. So now I hope you would have understood that these two are interrelated concepts. If these two are happening simultaneously, they give rise to a transverse wave as electromagnetic wave. Okay. In this electromagnetic wave, there are certain important points to be kept in your mind. The time varying electric and magnetic fields. What is happening? The time varying, this is an important point to be noted. The time varying electric and magnetic fields, which are mutually perpendicular to each other, they are also perpendicular to the direction of propagation. So what they are trying to say is, if electric field is along y direction, magnetic field is along z direction, then they are perpendicular to each other along with the direction of propagation. So this is another important point to be noted. Okay, so the concept of displacement current, I will discuss it later. Now we will discuss about the source of an electromagnetic wave. Okay, so we will discuss about the source of an electromagnetic wave. Right. So what should happen is, please make a note of this point. If somebody asks you how are electromagnetic waves generated, you need to write this. So electromagnetic waves are generated by electrically charged particles oscillations. Means if there is an accelerated charged particle, okay, to put it in simple terms, I will also call it as accelerated charged particle. If there is a charged particle which is put into oscillation, then you can generate an electromagnetic wave. Okay. So how is it happening? We will see it. If there is any doubt, please ask us. Am I clear with this point? If somebody asks you what is the source of an electromagnetic wave, what will you say?
Electrically charged particle oscillation.
Yes, you need to put an electrically charged particle into oscillations. In simple terms, you can also call it as accelerated charge particles. It means if the charge particles are put into oscillation, they tend to accelerate and they give rise to electromagnetic waves. So how is it happening? I have an explanation for it. I'll come to that. So the electric field associated with accelerating charge particle will generate vibrating magnetic fields, and these vibrating electric and magnetic fields give rise to electromagnetic waves. Okay, let's see the explanation. See, one thing is clear for me, guys, that I need to generate both electric and magnetic fields simultaneously. So till now we know the fact that if there is a static charge, you have what region around it?
Electric field.
You have a region of electric field around it. Is there a possibility of magnetic field in this scenario?
No, sir.
No, sir.
Right. So we are going to take different permutations and combinations. What did I say? You have a charge particle and it should accelerate. Now we are going to slightly touch the motion chapter and come. See, what are all the different positions we know? One is rest and the second is motion. So when I talk about motion, there are two kinds of motion I can talk about. What are they? One is called as uniform motion. So what do I mean by uniform motion, guys? Uniform motion means constant velocity, or I can call it as non-uniform motion where the object is accelerating. Okay, so initially, if you, so this process I'm going to follow to understand why we need a charged particle to accelerate. Okay, so if the charged particle was at rest, what would have happened? Electric field associated with the charge will also be static. So there will be no generation of electromagnetic waves, as electric field is not varying with respect to time. What did I say? Electromagnetic waves are the ones which are time variant. So the first point fails. Now, what will happen when the charge is moving with a uniform velocity? Then what would have happened? Then acceleration would have been zero. Accept it. So the change in electric field with respect to time will also be constant. As a result, what will happen? If there is a charged particle, guys, okay, if there is a charged particle which is put into motion with a constant velocity, then what would have happened?
It will get displaced, sir.
So it will get displaced, first thing. So what will happen? There is a region of electric field around it. Correct? There is a region of electric field around it. Imagine if the charge is here, then the new position of the region of electric field would have been here. Means the electric field will also move with respect to charge. And secondly, what is happening? The change in electric field with respect to time will be a constant. Okay, the relative change will be a constant. Then what will happen? You cannot produce a time varying magnetic field, because what is the first point that we saw, guys? What is the first point? A changing magnetic field will generate, changing electric field will generate a changing magnetic field. But what is happening due to the constant velocity? If there is a uniform velocity to the particle, then acceleration is zero. When acceleration is zero, the change in electric field with respect to time is also constant. So it is not a time varying one. So since it is not a time varying one, it can still not generate an electromagnetic wave, because magnetic field is not a time varying one that is going to get generated. So what should happen? Hence, it is clear that only accelerated charged particles can generate electromagnetic waves, because when the particle is accelerated, then the electric field will be a time variant one. When electric field is time variant, magnetic field will also be time variant. So electric field will give rise to a time varying magnetic field, and the vice versa will happen, as a result of which EM waves will get generated. So you can ask me, sir, accelerated charged particles would have been sufficient for us. No, since we have assertion reason based questions, either of these things can be asked. So whatever I explained in the explanation can be asked as an assertion. So at that point, you should not struggle. Okay, I want you to have a clarity about that. Is it clear, guys?
Yes, sir.
Right? So the important note to be kept in mind here is, if you have, see, don't get confused between these 2 points, okay? You remember the concept of simple harmonic motion? At least you would have remembered the term simple harmonic motion. So what
Yes, sir.
exactly is simple harmonic motion? If there is a charged particle put into vibration or oscillation, do you remember the fact that the charged particles will accelerate, which is given by the equation minus omega square x? So acceleration of the charged particle, acceleration of the particle which is oscillating is given as minus omega square x. So what I'm trying to say from here is, whether you use the word oscillating charged particle or accelerated charged particles, they mean the same. Because oscillating particles will always tend to accelerate. I hope I have answered the question, right? So the last point that we are going to discuss today is, if you have an oscillating charged particle that will have an oscillating electric field, which gives rise to an oscillating magnetic field. Okay, that is first point to be noted. Second, oscillating magnetic field in turn gives rise to oscillating electric field, and so on, and this process continues. So what is the first point telling? If there is an oscillating charged particle, what will get generated first? First thing that will get generated is oscillating electric field, and that oscillating electric field will give rise to oscillating magnetic field. Since this oscillating magnetic field has got generated, what will it try to do? This oscillating magnetic field in turn gives rise to oscillating electric. This oscillating magnetic field will again start giving rise to an oscillating electric field, and so on, and this process continues. So regeneration of electric and magnetic fields are same as the propagation of the wave, and this wave is what is known as electromagnetic wave. Here one important point to be noted is, this electromagnetic wave has different parameters associated with it, like time period, frequency, and all those things. So if we will be concentrating on 2 important factors in this chapter. One is frequency and the second is wavelength. Okay. So based on the frequency and the wavelength associated with a particular wave, they are classified into different segments in the electromagnetic spectrum. That we will see later. Okay. So I hope you are able to understand what I mean by frequency. So since it's a wave, it has a frequency, means the number of times it is oscillating with respect to number of times it is oscillating per unit time. So frequency of electromagnetic waves in this case is exactly equal to the frequency with which you put the charged particle into oscillation. Means if you need to generate a particular frequency, to call it, let's say, as a visible light or a radio wave or a microwave or whatever you call it, you need to put the charged particle into vibration with that particular frequency of what you require. Are you able to understand? So this is all about the basic introduction of what an electromagnetic wave is and what is the source of an electromagnetic wave. So these are all the points you need to have in your mind, guys. Right? So with this, I'll stop. And in tomorrow's class, please tell me.
The frequency of oscillating particle means each particle, sir, or on the whole, sir?
No. See, what is the source of an electromagnetic wave? How many charged particles do you need to put to generate electromagnetic wave?
N, sir.
No. Read the statement. Accelerated charged particle. One particle is enough. If you take one particular charged particle, only one, okay, and put it into vibration, okay, with a frequency of few kilohertz or few megahertz. So that is how the frequencies are. They are very high. Okay. If you are able to put one charged particle into that amount of frequency, you will be able to see an electromagnetic wave coming out of it. Okay. Means the process has to be that fast. So that is what I meant by frequency of electromagnetic wave is equal to the frequency of the oscillating particle. Means I'm talking about that one particular particle which is put into oscillation. Am I clear, Mithun?
Okay, sir. Understood, sir.
Understood? Yeah. So this is an important point. Please make a note of this. All these things can be asked in assertion tests. All these things can be asked. It is up to you to grasp it. Okay. Any other doubt? Don't wind up. Just give me a minute. I want to take screenshot of the attendance. Don't wind up. Okay. Yeah, you guys can leave. I'll see you all tomorrow.
Thank you, sir.
Thank you, sir.